Okay, next up, factoring some trig expressions. What I'd like you to get out of these two examples is that there's nothing different about factoring trig expressions. These two are not going to introduce any really new concepts. What I hope you get from this is that all the stuff you've learned about factoring in previous chapters when you've been doing polynomials and radicals and all those other things still works when you're doing trig. These expressions look a little different and they have Greek letters in them, but it doesn't really change the way you factor. So, when you first see an expression, the very first thing you always look for when you're factoring is common factors, and we have one. We have a common factor of 3. We can pull that out, and it leaves us with cosine to the 4th theta minus sine to the 4th theta. Or if you read this cosine theta to the 4th or sine theta to the 4th, people will generally understand that too. Now, can this be factored any further? Actually, I'll give you more than that. This can be factored further. How? It's a difference of squares because this is a perfect square. It's something to the 4th power. And this is also something to the 4th power. So we can split this up like a difference of squares. Two big brackets with a plus and a minus. The square root of this piece, which is cosine squared, goes in the first spaces. And the square root of this piece goes in the second spaces. So sine squared theta and sine squared theta. We can go even one more step. Do you see why? We pull this thing apart. Cosine squared minus sine squared is another difference of squares, so we can break that down. The cosine squared plus sine squared, well, I was about to say that there's nothing we can do with that, but there is something, isn't there? Do you see it? Think Pythagorean. Cosine squared plus sine squared just makes 1, so that entire term drops out, which is nice stuff. This is a second difference of squares, as I mentioned, so we can split that up, put a plus and a minus, and cosine squared would have come from cosine theta times cosine theta, and our sine squared would have come from sine theta times sine theta. Of course, you could just toss that 1 and just say it's 3 times cosine plus sine times cosine minus sine, and that's as factored as that thing will get. Okay, here, what do you think? The very first thing you should be looking for is common factors, always, and there is one. Both of these terms contain sine squared theta, so let's pull that out and see what remains. Sine squared theta out leaves us with 1 plus cotangent squared theta. Now, is that a Pythagorean identity? I confess that I don't remember. It looks like one to me because it contains a squared trig operation and a 1, but I'm having to peek here at my identity list and I see that, yeah, it is. 1 plus cotan squared is equal to cosecant squared. So we can clean this thing up like so. Sine squared theta, and 1 plus cotangent squared makes cosecant squared theta. That's looking pretty good, but it would be an awful shame to stop there. Do you see why? There's a way we can take it further. Sine squared theta. Cosecant is 1 over sine. So this expression is really 1 over sine squared theta. Well, now, the signs cancel out. All that remains of this entire expression is 1, and it don't get any more factored than that.